All right, so we're going to take a look at a pretty involved example. There's a lot of parts to it, but it's a really good example to take a look at because there are so many parts to it, because it explores so many different aspects of this section that we're trying to kind of understand. So let's take a look here. This is in your textbook. This is example 3 if you have the book, if you want to take a closer look at any of the work there. Says, suppose we have the price-demand equation x equals 10,000 minus 1,000 p, where x is the number of units demanded at price p, and the cost function c of x equals 7,000 plus 2x. So we're going to start this problem by finding the domain of the price-demand equation. So we're given x equals 10,000 minus 1,000 p. And I want to start this problem by taking this equation and solving it for p, actually. I'd like to be able to say, okay, this is the price based on how many units are being demanded. So I'm going to start here. Let's add 1,000p and subtract x from both sides. So 1,000p equals 10,000 minus x. And then I'll divide everything by 1,000. And the way I'm going to do that over here, just so that it works out a little bit better, I'm going to divide 10,000 by 1,000, and then I'm going to divide x by 1,000. So here what I end up with, I've got p equals 10,000 divided by 1,000. I should have 10 minus, here this is really 1 over 1,000 here, 1 over 1,000. So you could leave it as a fraction, you could leave it as negative x over 1,000, but I know that there's a lot of us out here that are not the biggest fans of fractions. So another way we could write it is take 1 divided by 1,000, which is 0.001 times x, and this is my price-demand equation in terms of x. So here's my price-demand equation. Now I'd like to talk about the domain of this function. So the domain talks about the values of x that make sense for our problem. So a few things will be helpful for us. The first is to remember that x is the number of units demanded here. I'm going to assume that there is always a positive, or rather at least a non-negative number of units demanded. So on the one hand, I'm going to say, well, x should be greater than or equal to 0. The other thing I need to think about is, okay, well, the other piece of this puzzle that I have right here is price p. And I found that in most successful businesses, they charge a positive value here. So I'm going to say my price should be greater than or equal to 0 as well. But my price, I want to write my domain in terms of x. So my price, which is equal to 10 minus 0.001x, should be greater than or equal to 0. So I'm just going to solve this inequality pretty quickly for x. So let's see, negative 0.001x greater than or equal to negative 10. So I should have x is less than or equal to 10,000 here. So essentially this says x should be greater than 0 but less than 10,000. So I want x to be between 0 and 10,000. So my domain here would be 0 to 10,000. So there is the domain of our price-demand equation. Part B says we want to find and interpret the marginal cost function, which is c prime of x. So let's go find c prime of x. So we were given that c of x here, c of x is 7,000 plus 2x. So when I go to find my derivative, c prime of x, well, the derivative of 7,000, that's just a constant, so derivative of 7,000 is going to be 0. And derivative of 2x is just going to be 2, so c prime of x is 2. So this is a little bit different. I don't think we've seen one like this here in this section. So I found the marginal cost function, but we have a new problem here. We want to interpret this marginal cost function as well. So how could I think about this? Well, if I look at this, what's different about this problem is it's just 2, right? My marginal cost function is simply just 2. It does not depend on x. This isn't, 2x squared plus 4, anything like that. It's just, get rid of that, it's just 2. So what this means is that the cost is, and again, when I talk about marginal cost or marginal revenue or marginal profit, whatever it may be, I want to pay attention to the sign here of our marginal cost or revenue or profit. So this is in particular a positive too. So the cost is increasing by $2 per unit. So this is how we would interpret. We interpreted marginal cost in the last example here. We said, okay, the cost is increasing by this amount per unit, but we also haven't mentioned our production level. But if you look at C prime of x, it actually doesn't depend on x, which is our production level. It doesn't depend on your production level. So I would say the cost is increasing by $2 per unit regardless of production level. So it doesn't matter if you're making 100 of these or 100,000 of these. Your cost is always going to be increasing by $2 per unit. So in a way that might be nice to know that it's always increasing by a constant amount. It maybe makes it easier to predict. Part C, I want to find the revenue function as a function of x and find its domain. So I want to find r of x. So what does revenue depend on? So revenue is the amount of money that you take in sales. So it's just the amount of money that you take in sales. We're not considering cost yet. So the amount of money that I make in sales, for r of x, this is going to depend on the price that I sell my product at, as well as the number of units sold here. Number of units sold here, or the price times the quantity, sometimes we say. So the price, I know that's just P. And number of units sold, or that's the same as the number of units demanded here, that's x. So my revenue function, r of x, is P times x. This would be a good formula to memorize because it will be one that we reference pretty often in this class. So the revenue is always P times x. Well, I wanted the revenue function as a function of x right here. So I can't just leave it as P times x, but luckily for us, earlier we said, hey, our price demand equation is right here. It's P equals 10 minus 0.001x. So I'm going to take that 10 minus, here, let's do this right here. 10 minus 0.001x times x. I'm just going to take out that P and replace it with this side of my equation over here. And then, okay, sure, we can distribute the x. Let's go ahead and do that. I have 10x minus 0.001x squared. So here is my revenue function in terms of x. That's the first part that I was looking for. The next part I was asked to do, it says, and find its domain. So there's a few different ways you can think about this. One is to take your revenue function, take your r of x, and say your revenue is solely the amount of money you take in. So it really only makes sense that you make a positive, or at least a non-negative amount of money in sales. So you could take this and set up an inequality, and you could do that, but it's actually a little bit more work than the alternative. The easier way to look at it is to look at, well, what is revenue dependent on? Revenue is dependent on price. Revenue is dependent on quantity. So we want P to be greater than or equal to 0, and we want X to be greater than or equal to 0. Hey, look at this. These are the exact same constraints we came up with way back in Part A. So what that tells me is that the domain of my revenue function is actually going to be the same as the revenue of my price demand equation. So I can just say, hey, you know what, this is also the revenue for the price demand equation. And that makes sense, right? We built the revenue function using the price demand equation. It relies on it. So it kind of makes sense that the domain of the revenue function should also depend on the revenue of the price-demand equation. So my domain here in this case would be 0 to 10,000. Cool. So it's the same exact domain. I have my revenue function. I think I've got everything I need here. Part D says find the marginal revenue at x equals 7,000 units and interpret these results. So here, marginal revenue, marginal means derivative, right? So first of all, I want to find r prime of x. So referencing, let's just write down r of x actually, just so that we have it in front of us. R of x is equal to 10x minus 0.001 x squared. So r prime of x, derivative of 10x would be 10, minus over here using my power rule, I've got negative 0.002 times x. So this is my revenue function. I want to take 7,000 and I'm going to plug this in for my revenue. So let's see. R prime of 7,000, I'm going to plug this in for x. 10 minus 0.002 times 7,000. So I have 10 minus here, I should have 14,000. Oops, no, excuse me, no, just 14. Just 14. 10 minus 14 gives me a negative 4. So now I've found the marginal revenue. Here's part of my answer. My marginal revenue is negative 4. But more importantly is this interpretation. I want to be able to talk about what this number means. So when we're talking about marginal whatever, whether it's marginal cost or revenue or profit, again, I always like to refer to your production level. Here, x equals 7,000 is our production level. So I would start this interpretation, I would say at a production level, of 7,000 units. And is this, did they say units per week? I just want to check. They didn't give us the amount of time, so I'm just going to say at a production level of 7,000 units, the revenue is here. I'm going to look at the price right here. Here, or excuse me, I'm going to look at the sign of the revenue function. I apologize. I'm going to look at the sign of my revenue function, which is negative. So in this case, the revenue is decreasing because our rate of change is negative. The revenue is decreasing by $4 per unit. So if I'm in a management position and I see that at this particular production level, the revenue is decreasing by $4 per unit, if I'm only interested in the revenue here, I might say, you know what, let's not increase our production, because if we increase our production, it's going to decrease our overall revenue here. So there we go. We have our marginal revenue. We have our interpretation. Part E, this is a little bit different this time around. This is actually kind of a college algebra problem, but it's good to kind of come back and revisit this. It says graph the cost function and the revenue function on the same coordinate axis system. Find the intersection points of these two graphs and interpret the results. So what I want to talk about here is I want to just kind of get a rough sketch. This does not need to be particularly detailed. I really just want an idea of what these two graphs look like. So I'm going to start with my cost function here, because the cost function is going to be easier to look at. My cost function, just so that I can write that down here, C of x, I believe we said 7,000 plus 2x, but let me double check. Yeah, 7,000 plus 2x here. So my cost function is 7,000 plus 2x, and then my revenue function, will do that in just a second. My revenue function, r of x, we said that was 10x minus 0.001x squared. So let's start with our cost function here. I look at this, I see a positive y-intercept here of 7,000, and I see a positive slope of 2. So I'm just going to give an idea of what that looks like. A positive y-intercept, let's say it intersects right there, and a positive slope, that means my function should be increasing. So perhaps my function looks something like this. It does not need to be particularly detailed. I just want an idea of what's going on here, because at the end of this problem I want to come back and kind of think about what each region of our graph represents. So here we have our cost function. Our revenue function. Now our revenue function, if you were to take this function, it would probably be helpful if you were to take this function and set it equal to 0. And if you did, you would end up with 0 and 10,000, which means it's going to intersect right here and right here. And again, I just want to think about, what do I know about my revenue function? Well, my revenue function, first of all, it's a quadratic function. It's x squared. And what do I know about that? So it's a quadratic, it's a parabola, and the leading term in this case is negative. That x squared term has a negative coefficient, which means it opens downward. So I know that my revenue function, it's a parabola that opens downward, and it passes through this point here and this point right here. So what does it look like? It might look something like this. Oops. Something like this, let's say. And this at least gives me an idea of what we're talking about here, an idea of kind of the range of values of what's going on here. So I have at least my sketch here. The other thing I was asked to do was to find the intersection points of these two graphs. So if I'm looking for what is this point and this point, what are those coordinates? So for those, I'm going to take these two functions and set them equal to each other, because if they intersect, that means they have the same x value and the same y value. So here, I'm going to take, let's do this in blue here. I'm going to take my cost function, c of x, and set that equal to my revenue function. So I have 7,000 plus 2x is equal to 10x minus 0.001x squared. So here I'm essentially just trying to solve this equation. I have a quadratic equation right here. And the easiest way to solve a quadratic equation is to take this and set it equal to 0. I prefer my x squared term to be positive, so I'm going to take these two terms and move them to the other side. So let's see, when I do that, I've got 0.001x squared, 2 minus 10, I've got minus 8x, plus 7,000 is equal to 0. From here, how you solve it, again, you could factor it. You'd have to be pretty good at factoring it, though. I think it would be pretty tricky here. Completing the square. Usually if something doesn't factor, though, I'm going to jump straight to the quadratic formula. So quadratic formula, just so that we recall, and let me maybe do this in a different color. Quadratic formula is x equals opposite b plus minus square root b squared minus 4ac all over 2a. So in this case, x is equal to opposite b, so opposite negative 8 would be positive 8, plus minus negative 8 squared, minus 4 times a is 0.001, times c, that's 7,000, all over 2a, that's 2 times 0.001. And now we just need to be careful with our arithmetic here. 8 plus minus square root negative 8 squared, I've got 64 there. Here, let's see, 7 times 4 minus 28 here. Yeah, that looks good. All over 0.002. So let's see, I've got 8 plus minus square root of 64 minus 28. That should give me 36 all over 0.002. So this gives me 8 plus minus 6 divided by 0.002. So I really have two solutions here. I've got 8 plus 6 and 8 minus 6, all divided by 0.002. So I have 8 plus 6 divided by 0.002, 8 minus 6 divided by 0.002. So here I've got 14 over 0.002, which would give me 7,000. And here, 8 minus 6, I've got 2 divided by 0.002, which would be 1,000. So these are my x-coordinates. The other thing I might want, it said find the intersection points, right? It didn't just say find the x values where these intersect. It said find the intersection points. So I'm going to take these two x values, this x equals 7,000 and x equals 1,000, and I'm going to plug them into, and actually, and this is kind of interesting, it doesn't actually matter whether you plug it into the cost function or the revenue function, because we started off by assuming, you know what, let's assume that these two are equal, because that's how you have an intersection point. So you can plug them into either the cost function or the revenue function, whichever you think is easier. I happen to think that the cost function is going to be easier to work with. So C of, let's say, 7,000 is equal to 7,000 plus 2 times 7,000. So let's see, this is 14 plus 7, 21,000. And C of 1,000 is equal to 7,000 plus 2 times 1,000. Oops. And this is equal to 9,000. So I have my intersection points. I have 7,000, 21,000, and I have 1,000, 9,000. Okay, so I've got my intersection points. That's the most involved part of this problem. It also says interpret the results, interpret what these are. So these 2 points, this is where the cost function is equal to the revenue function. So here's the 2 points that I just found where the cost function is equal to the revenue function. So if we have these points where we have the cost is equal to the revenue, we call these break-even points. Because usually that means it's where you break even. That means where you kind of overcome your initial costs and you begin to make a profit. But break even in this case could be a bad thing as well. Sometimes these are called equilibrium points as well. Some books just define it differently. Last thing I want to talk about for this problem, it didn't ask me to do this, but I want to just mention it very briefly here. I want to look at each section right here. Because when I look at this graph, I really see 3 distinct parts. I see this little piece right here, see all of this stuff right here, and then I see this spot right here. So I want to take each one of these and talk about them. So let's start with this little piece right here. So remember that this red graph right here, I said this was my revenue function R of X. So what's going on in this region right here? Well, I have my cost function, which is that black line, is higher than my revenue function, this red line right here. So what that means is if we're anywhere in these x values right here, the cost is higher than the revenue, which means I'm spending more money than I'm making. So in this case, this represents a region of loss. That means you're losing money overall. So we would not want to be here if we were the business owner. Then we've got this big middle ground right here. So what's going on right here? Well, in this case, the revenue function, the red parabola, is higher than the cost function over here, which means I'm making more money than I'm spending. If I'm a business owner, this is good. This means I'm turning a profit right here in this region. So that is where I'd like to be. I'd like to be at a place where my revenue is higher than my cost. And then finally over here, we see this switches once again. Here I have the cost function is higher than the revenue function. We don't want that because that represents a region of loss. That means I'm spending more money than I'm making. So really, we found these two x values. We said 1,000 and 7,000. We want to be manufacturing somewhere between 1,000 and 7,000 units because that's where we're going to turn a profit. We want to be in this big middle section right here. That's how we're going to make money. So very cool. Just a nice way to review some terminology, review some old algebra skills, and even graph a couple functions. Part F here, we want to find the profit function. So I want to find the profit function. The profit function, it's really easy to mix up with the revenue function because they're very similar. The profit function is how much money you get to take home at the end of the day after you pay your bills, after you take out your costs. So it's the amount of money that you bring in revenue, take away your overall costs right here. So it's just the revenue function minus the cost function. So your revenue function, we had 10x minus 0.001x squared. Here's our revenue function. Minus our cost function. Our cost function we said was 7,000 plus 2x. And notice I used parentheses around each of these. And I did this for more than one reason. First of all, I think it just makes it very clear the separation. Here's my revenue function, and here's my cost function. It makes it easier for the reader to determine kind of what is what here. What substitutions have I made? But there's a second, more practical application, and it's because of this minus sign right here. I need to subtract this 7,000 and this 2x over here. And if we don't put parentheses around it, it's really difficult, if not impossible, to remember that, hey, this minus sign needs to go over here as well. I'm actually subtracting this 2x. So what I like to do here is I like to distribute that minus sign. I don't like subtraction. I always turn it into plus the opposite. So I'm going to change the sign on each of these. And I think this just makes it a little bit nicer to work with. So negative 0.001x squared. What else do we have? We've got 10x plus negative 2x. So that'll be plus 8x. And minus 7,000 right here. This is my profit function, P of x. Lastly, for this problem, I want to see if I can find the marginal profit at x equals 1,000 and then talk about the results. So again, I see we're talking about marginal profit right here. Again, that word marginal should hopefully start to be linked in your mind with the derivative. So I need to find the marginal profit function first and then take 1,000, plug that in, and then just talk about what that number means. So first let's find P prime of x. We'll just be using our power rule. So negative 0.002x plus 8, derivative of negative 7,000, that's just a constant, so that'll be 0. So here's my marginal profit function. I want to evaluate this at 1,000 here. So this is equal to negative 0.002 times 1,000 plus 8. So here at P prime right here, P prime of 1,000, I have negative 0.002 times 1,000. That should be negative 2,000. Oops, excuse me, no, I'm sorry, my mistake, negative 2. I'm trying to do too much math in my head here. Negative 2 plus 8. Negative 2 plus 8, here I have a positive 6. So what does that mean for me? So again, I'm going to start this interpretation by talking about my production level right here. At a production level of 1,000 units, we're talking about marginal profit right here. So the profit is, and here's where we want to pay attention to that sign. We had a positive 6 right here. Positive 6, that means my rate of change is positive, means that the profit is increasing by $6 per unit. So that means that if I'm in this position, if I'm currently manufacturing 1,000, if all I care about is profit at the end of the day and I have the means to increase production, then yeah, I absolutely should, because if I increase my production, right now it's going to increase my profit by about $6 per unit. So that would be good for me as an end result. So take a look at a handful of these problems. What I'm really interested in is you being able to find marginal cost, revenue, profit functions and then talk about what they mean. That's going to be the type of question that I ask you on the quiz or the exam.